Welcome back. Now we are launching into a new chapter, Chapter 5. But it's actually very similar to the last one, Chapter 4, because it focuses on eigenvalues and eigenvectors to analyze nonlinear systems of differential equations. Okay, so let's look at the trace-determinant plane. You may think, trace-determinant plane, never heard of that. Well, it's actually a tool we use to analyze the different types of behaviors. So let me go back to how we've related the trace-determinant before. We had three cases when dealing with the linear homogeneous equations. We first had the trace squared of the matrix greater than 4 times the determinant of A. And this is the type where we had distinct real eigenvalues. Then we had trace squared of A equals 4 determinant of A. This was the currently case 3, previously case 2, 1. So we'll just put it second. With the duplicate real eigenvalues. And then we have the trace squared of A being less than 4 times the determinant of A. And that's where we have the complex conjugates. Okay, so those are the three types based upon the solution techniques. But these three types actually break down a little bit further in terms of behavior of the solution. So I'm going to draw the trace-determinant plane, or a graph that helps me analyze the combinations of these two things, the trace squared and the determinant of A, in various combinations. So I first have my axes and I determine which one is which. Well, this relationship, trace squared of A equals 4 determinant of A, can be either solved for the trace as 2 square roots of the determinant, or it can be solved for the determinant as 1/4 of the trace squared. And it's easier to draw quadratic. So we end up treating the determinant of the matrix as our y-axis, and the trace of the matrix as our x-axis, or x and t if you'd rather. Now let's look at where this curve comes into play. Let's make it a little less wide so we can see more of the pieces. Okay, so there is the trace squared of A equaling 4 determinant of A. Hard to see that. Let me erase it. Try that again. This is where the trace squared of A equals 4 times the determinant of A. Another way to think of that is the determinant of A equals 1 as the trace squared of A divided by 4. So 2 ways to define the same quadratic. Now along that line, we have the duplicate real roots. And those duplicate real roots are either positive when the trace of A is positive, or negative when the trace is negative. since we know that the trace of the matrix equals the sum of the eigenvalues, and the determinant of the matrix equals the product of the eigenvalues. So the question is whether or not the solution based upon those eigenvalues will be stable in the sense that it converges to some value or is bounded, or unstable where it diverges to infinity. Well, if the two roots are positive roots, positive sum, then let me see. Then it is unstable. I'll use a red to represent unstable. So if the two roots are both positive, then we know it's unstable. The exponentials are going to infinity. If the two roots are negative, I have a negative sum. And we have stable solutions where the exponentials will both go towards zero. We have a finite steady state. And right in between, we don't quite know. So we'll put a little open circle right in the middle between the stable duplicate roots and the unstable duplicate roots. Then we have the duplicate real roots. Well, this is where, the distinct real roots. This is where the trace squared is greater than 4 terms of A, or the determinant of A is less than a quarter of the trace squared. So the distinct real roots are down here. So this is where we have real solutions down the bottom, which makes the inside piece or upper piece the non-real complex conjugates. Well, on this part where it's real, we have a trace that's negative, so the sum is negative, but the product is positive. So if the sum is negative and the product is positive, they're both negative. So this is stable. Stable sink. And that stability goes all the way down to the edge, bottom edge, where the determinant is 0. When the trace is negative and the determinant is 0, that means that one of the eigenvalues is 0. So we have a stable edge to it. So this is one region of stability where it is real and shooting in towards a sink. We'll take a look at what shape or behavior we get there, but it's exponential, and you can think of this in terms of a star coming together, imploding in a sense. So solutions that look more like that. Now, what happens when we go down to the bottom? Well, the determinant becomes negative, but the trace is still negative. The determinant is now negative, which means the two eigenvalues add to a negative value, but they multiply to a negative, which means one has to be positive, one is negative. We call this a saddle. And these are semi-stable. So saddles are where you have certain directions that pull in and certain directions that pull out. So if we take some point or pulling in along one direction and pushing away along another. So slight difference between our star where it's pulling in multiple directions. And as you shift from a saddle on the left to a saddle on the right, we move from the sum is negative to the sum is positive, which means the larger eigenvector is pushing away and the smaller eigenvector is pulling in. It looks basically the same, only they're inverted. Now the directions here I've just drawn arbitrarily, so it doesn't happen to be a 45-degree angle and a negative 45-degree angle. That's just an arbitrary statement of it. Often we will have that kind of relationship where they're about 90 degrees or similar to, but not always. What is for sure is that we'll have a line that pushes away and a line that pulls in. That is true. That's based upon the eigenvector. This is all possible multiples of a certain eigenvector. This is all possible multiples of another eigenvector. And so this whole bottom region is semi-stable saddles. Then we move up. We cross into having a positive determinant, but a positive trace, which means both eigenvalues are positive. We're shooting away. That is called an unstable node, but because it's shooting away in all directions, we call it a source. And it could be balanced, where they're pushing away an even balanced directions, or one could be pushing away stronger than the other. Like that. And this boundary is unstable, where we have one positive eigenvalue, one zero eigenvalue. So we have a stable sliver, stable sink, where it's just converging in. We have a semi-stable region where certain directions are stable, certain directions are stable, certain directions are unstable. And then we have an unstable sliver based on sources. So those are all the real types of behaviors. And in the table, they label them one, two, three for sinks. And then we have three more regions that describe the complex conjugates. And that would be 4, 5, and 6. So let's look at those. 4 is on the determinant axis where the trace or sum of the eigenvalues is 0. Now, if the eigenvalues are complex conjugates, the sum being 0 means the real part is 0. So if R1 and R2 equal alpha plus or minus beta I, then the trace of A equals 2 alpha, and the determinant of A equals alpha squared plus beta squared. So the determinant has to be positive for us to have complex conjugate eigenvalues, but the trace tells you the alpha, the real part. And the real part tells you the exponential, whether it's increasing if alpha is positive, or whether it's decreasing to 0 if alpha is negative, or if it's 0, whether it's just orbiting around and oscillating back and forth with cosines and sines. So we describe this middle area as a stable region, but it is very close to being unstable. It's not quite like a saddle where it's semi-stable, it's actually stable. But it's just a line. It's more like this line than a whole region. And in that line, we have solutions that go around each other. They just orbit around some point in the center. So we call these centers. On the left, we have a stable region. We call these they are stable. We call them spiral. To call them a spiral sink because they are spiraling in to a point. On the other side, we have spiral sources. And the direction doesn't matter. Well, the direction can be determined by the eigenvectors, but for this purposes, I'm just choosing a direction for the rotation. These are unstable. And we call them each a spiral source. And right in between, we call this a center. Whew, that got complicated fast, didn't it? So let me take a minute here and clean up all this information and label it simply based upon the shape of the behavior. So I'm going to erase this table over here. And draw a smaller version of this, a more succinct version of this trace-determinant plane. So saddles. Like that. Sources. We'll just do a linear combination there. They can be bent in terms of the imbalance between the exponentials, that's fine. And right in the middle, our centers. So here is a more succinct form of the trace-determinant plane describing the behavior of our major 6 regions and other pieces. So we have the saddles, the semi-stable region down the bottom. We have the stable sinks and the stable, the sinks and the spiral sinks, which are our region of stability in this second quadrant. We have the spiral source and the sources that are our region of instability in the first quadrant. Those two are separated by this very delicate center. And they are both bounded by this semi-stable region of saddles down the bottom. I wanted to point out that I've posted a few videos that are graphical demonstrations of some of the concepts in Chapter 5 that are produced by Dr. Mitchell, a colleague at Stephen F. Austin State University in Texas. He has done an excellent job on creating these MATLAB GUIs, basically, graphical user interfaces, to see both the trace-determinant plane on one side and the actual linear system, the p-plane, if you will, on the right-hand side, and a couple of other really neat graphical demonstrations of the ideas we've tracked through so far. Notice that he calls the spiral sinks and sources focus, and a stable focus and an unstable focus. So the foci, if you will, are different ways of saying spiral sink or spiral source. And then he refers to sinks and sources just by stable node or unstable node. And then, of course, saddle is the same. And center is the same. So a couple different slight changes in notation here, but I just want to point that out. I hope you enjoy, and I hope these graphical demonstrations are helpful for you.